The acid-base theory is one of the most important theories in chemistry. Acids were earlier to be recognized because of their sour taste. The English word, acid, is derived from Latin word meaning sour. Other properties at an early date with acids were corrosion to some metals, and the production of bubbles of carbon dioxide gas when they were applied to chalk, calcium carbonate. Bases, or alkalis, were characterized mainly by their ability to neutralize acids and form salts. The latter being typified rather loosely as crystalline substances soluble in water and having a saline taste. Today, we are aware of that, not all the salts are soluble in water. The first scientific concept of acids and bases was provided by Lavoisier. Since Lavoisier's knowledge of strong acids was mainly restricted to oxoacids, such as nitric acid and sulfuric acid, which tend to contain central atoms in high oxidation states surrounded by oxygen, and since he was not aware of the true composition of the hydrohalic acids, he defined acids in terms of their containing oxygen, which in fact he named from Greek words meaning acid former. Sir Humphrey Davy proved the lack of oxygen in hydrogen sulfide, hydrogen telluride, and the hydrohalic acids such as hydrochloric acid. However, Davy failed to develop a new theory, concluding that acidity does not depend upon any particular elementary substance, but upon peculiar arrangement of various substances. Just as von Liebig proposed that an acid is a hydrogen-containing compound whose hydrogen can be replaced by a metal. His ideal was based on the fact that some acids, such as sulfuric acid, react with some metals, such as magnesium, to produce hydrogen gas. The first modern definition of acids and bases was developed by Arrhenius. An Arrhenius acid is a substance that dissociates in water to form hydrons. A hydron is the general name for a cationic form of atomic hydrogen. The term hydron includes cations of hydrogen regardless of their isotopic composition. Thus, it refers collectively to proton, deuteron, and triton. Since the natural abundance of proton is 99.98%, we limit our discussion to proton for simplicity. Thus, an acid increases the concentration of the proton in pure water. However, today, we know that a bare proton does not exist in aqueous solution. It combines with water to form a hydronium ion. Nevertheless, conventionally, we can still call a hydronium ion a proton, if no ambiguity is made. For example, hydrochloric acid is a typical monoprotic Arrhenius acid, which dissociates to produce one proton per molecule. Sulfuric acid is a typical polyprotic Arrhenius acid, which dissociates to produce up to 2 protons per molecule. In this section, our discussion is limited to aqueous solutions, so all the notations of phases, such as L and AQ, are omitted unless other specified. An Arrhenius base is a substance that dissociates in water to form hydroxide ions. It increases the concentration of hydroxide ion in pure water. An Arrhenius base is also called an alkali. Alkalis are usually hydroxides of alkaline and earth alkaline metals. For example, sodium hydroxide and barium hydroxide are typical alkalis. An acid-alkali reaction is such a reaction, where an acid reacts with an alkali. The products are a salt and water. Acid-alkali reactions are also known as neutralization reactions. In general, acid-alkali reactions can be simplified to the reaction between proton and hydroxide ion by emitting spectator ions. Different types of acids can donate different numbers of protons per molecule. A monoprotic acid is an acid which dissociates to give at most 1 proton per molecule. Typical monoprotic acids include hydrochloric acid, nitric acid, and acetic acid, etc. Pay attention, not all the hydrogen atoms in an acid molecule can ionize in dissociation. For example, hypophosphorus acid has 3 hydrogen atoms. But it is a monoprotic acid. A polyprotic acid is an acid which dissociates to give 2 or more protons per molecule. Typical polyprotic acids include sulfuric acid, which is diprotic, and phosphoric acid, which is triprotic, etc. Polyprotic acids dissociate stepwise. For example, carbonic acid dissociates to donate 1 proton in the first step, and dissociates again to donate the other proton in the second step. A monoprotic base is a base which dissociates to give at most 1 hydroxide ion per molecule. Sodium hydroxide is a typical monoprotic base. A polyprotic base is a base which dissociates to give 2 or more hydroxide ions per molecule. Barium hydroxide is a typical diprotic base. Arrhenius acid-base theory only works in aqueous solutions. Brindstede-Lowry theory is based upon the idea of protonation of bases through the deprotonation of acids. That is, the ability of acids to donate protons to bases, which accept them. Thus, the acids and bases are defined in pairs. In the general acid-base reaction equation, HA donates a proton to B. So, HA is a Brindstede-Lowry acid. B is a Brindstede-Lowry base. The deprotonation of an acid produces its conjugate base. A is the conjugate base of HA. The protonation of a base produces its conjugate acid. HB is the conjugate acid of B. In the reverse reaction, HB donates a proton to A. So, HA is the conjugate acid of A. Meanwhile, B is the conjugate base of HB. Brindstede-Lowry theory can be used in non-aqueous protic solutions, such as ethanol and liquid ammonia. Both Arrhenius and Brindstede-Lowry theories are used throughout this section, because they are compatible in most cases. Consider the following examples. When acetic acid is dissolved in water, it donates protons to water. So, acetic acid is an acid in both Arrhenius and Brindstede-Lowry theories. Water accepts protons. So, water is a base in Brindstede-Lowry theory but just a medium in Arrhenius theory. The acetic acid and acetate ion are conjugate acid and base of each other. Meanwhile, water and hydronium ion are the conjugate base and acid of each other. When ammonia is dissolved in water, it accepts protons from water. So, ammonia is a base, while water is an acid in Brindstede-Lowry theory. Ammonia and ammonium ion are conjugate base and acid of each other. Water and hydroxide ion are conjugate acid and base of each other. Though ammonia itself cannot be regarded as an Arrhenius base, it combines with water to form ammonia hydrate, which is an alkali. As you have seen here, in aqueous solutions, water can act as either acid or base in Brindstede-Lowry theory. In fact, water acts as acid and base simultaneously in any condition, because some water molecules donate protons, while some other water molecules accept protons. The ratio of water acting as acid to those as base depends on the protonation and deprotonation abilities of the solute. For instance, ammonia has a stronger protonation ability and weaker deprotonation ability than water. So, in the aqueous solution of ammonia, the fraction of water as acid is more than that as base. Meanwhile, the fraction of ammonia as acid is less than that as base. We know that a salt dissociates to cations and anions when dissolved in water. The cations and anions can further exchange protons with water. Such process is called the hydrolysis of the salt. A cation usually donates protons or accepts hydroxide ions, so it reacts as an acid. For example, in the solution of ammonium salt, the ammonium ion donates a proton to water to form ammonia and hydronium ion. An anion usually accepts a proton, so it reacts as a base. For example, in the solution of acetate salt, the acetate ion accepts a proton from water to form acetic acid and hydroxide ion. Amphoterism is a phenomenon that an amphoteric compound can react both as an acid and as a base, such as zinc oxide. Ampholytes are amphoteric molecules that contain both acidic and basic groups. For example, an amino acid has a basic amine group and an acidic carboxyl group, and exists as several structures in chemical equilibrium. Amphoproticity is a phenomenon that an amphoprotic compound can both donate and accept proton, such as water. So, amphoprotic compounds form a subset of amphoteric compounds. Partially dissociated polyprotic acids are amphoprotic ions. For example, bicarbonate ion is amphoprotic, because it not only donates proton to water as an acid, but also accepts proton from water as a base. In some protic liquids, the molecules undergo autoionization via the transfer of protons between the molecules of the same substance. Such autoionization is called autoprotolysis. For example, in liquid ammonia, one ammonia molecule donates a proton to another ammonia molecule to form an ammonium ion and an azonide ion. Thus, ammonia and ammonium ion are conjugate base and acid. Meanwhile, ammonia and azonide ion are conjugate acid and base. The liquid phosphoric acid undergoes a similar autoprotolysis. Water undergoes weak autoprotolysis. The equilibrium constant for water autoprotolysis is called water autoprotolysis constant, and is denoted by the symbol Kw. For pure water and dilute aqueous solutions, the activity of water is unity. So, water autoprotolysis constant is the product of the activities of proton and hydroxide ion. Water autoprotolysis constant depends on temperature. At room temperature, it is about 10 to minus 14. The equilibrium constants are usually too small or too large to be used conveniently. The operator, p, is usually used to simplify them. Applying p to a number, x, is defined as the decimal logarithm of the reciprocal of x. According to the properties of logarithm, pxy is equal to px plus py. Px to the power of y is equal to ypx. Thus, pKw at room temperature is 14. Similarly, the dissociation constants and solubility products can be denoted with pKd and pKsp respectively. All biochemical reactions and many other important reactions take place in aqueous solutions. The equilibria and rates of most of them are influenced by the acidity or basicity of the solution. Thus, pH scale is introduced to conveniently represent the proton activity. pH is defined as the decimal logarithm of the reciprocal of the proton activity. That is, p proton activity. In dilute solutions, the activities of solutes are approximately the numerical values of their molar concentrations. In pure water, the concentrations of protons and hydroxide ions are identical and very low. So, the activities of them are also identical. According to the definition of the autoprotolysis constant of water, the proton's activity is equal to the square root of water autoprotolysis constant. Then, the pH of pure water is half pKw. At room temperature, the pH of pure water is 7. Solutions with a pH of 7 at room temperature are neutral. Solutions with a pH under 7 are acidic, whose proton activity is greater than that of pure water and even greater than its hydroxide ion activity. Solutions with a pH over 7 are basic, whose proton activity is lower than that of pure water and is even lower than its hydroxide ion activity. A pH indicator is a halochromic chemical compound added in small amounts to a solution, which changes color when pH changes across certain values, so that the upper bond and/or lower bond of pH of the solution can be determined visually. A universal indicator is a pH indicator made of several halochromic chemical compounds that exhibit several smooth color changes over a wide range of pH. A universal indicator can be present in a form of a solution or paper. A pH indicator is usually a weak acid or base. It converts between conjugate acid and base depending on the pH of the solution, which show clear different colors. For example, methyl red presents in its acid form in pH under 4.4, which is red. It presents in its base form in pH over 6.2, which is yellow. Between 4.4 and 6.2, it looks orange as a mixture of acid and base, both of which are visible. Another example is phenolphthalein. It is colorless in pH from 0 to 8.3 and shows pink to fuchsia in pH between 8.3 to 10. The recipe of a simple universal indicator is thymol blue, methyl red, bromothymol blue, and phenolphthalein. It shows red in strong acidic, yellow in weak acidic, green in neutral, blue in weak basic, and violet in strong basic solutions. Typical solutions of different pHs are shown below. Gastric acid contains strong hydrochloric acid, so it is very acidic. Fruit juices contain weak organic acids such as citric acid. So, they are moderately acidic and taste sour. Baking soda contains sodium bicarbonate, in which the hydrolysis of bicarbonate ion is stronger than its dissociation. So, it is slightly basic. Bleach contains sodium hypochlorite. Since hypochlorous acid is very weak acid, its conjugate base, the hypochlorite ion, is a very strong base. That is why bleach is very basic. The acidity of an acid is measured by its dissociation constants, called the acid dissociation constants. Stepwise dissociation constants are each defined for the donation of a single proton. The equilibrium constant for the dissociation of the first proton is denoted as Ka1. The equilibrium constant for the dissociation of the second proton is denoted as Ka2, and so on. Pauling proposed that successive pKa values of a given acid increase. Thus, the acidity of an acid is mainly determined by its Ka1. Usually, Ka1 can be shortened to Ka. For example, the definitions and values of the stepwise acid dissociation constants of phosphoric acid are listed here. Suppose there is only one monoprotic acid in an aqueous solution. The definition of its acid dissociation constant is shown below. A strong acid is an acid with very large Ka, which is usually much greater than 1, so that its pKa is very negative. A strong monoprotic acid dissociates completely in its dilute solution. Thus, the proton activity is approximately its initial activity. For example, hydrochloric acid is a strong acid. The proton activity of 0.1 mol per liter hydrochloric acid is about 0.1. The pH of it is about 1. A weak acid is an acid with small Ka. The proton activity of a weak acid can be calculated using the equation for weak electrolyte. The pH of a weak acid depends on both its Ka and initial activity. The pH of a weak polyprotic acid can be calculated with the same equation, because its first step dissociation donates much more protons than the later steps. Let's use carbonic acid as an example. Please find the pH of carbon dioxide saturated water in ancient air. The partial pressure and volatility of carbon dioxide are provided. First, consider the Henry's law of the dissolution of carbon dioxide in water, from which we can find the initial concentration of carbonic acid. Then, use the formula for pH of weak acid. Here, though carbonic acid is a diprotic acid, its pH is determined exclusively by Ka1. The result is about 5.68. Normal rainwater is carbon dioxide saturated. So, it is slightly acidic, because carbon dioxide is a very weak acid. The carbon dioxide concentration in today's air is significantly higher. Nevertheless, normal rainwater is not too acidic. However, if the pH of the rainwater is lower than 5, the rain is called acid rain. Here, I show the locations of Ryolai and Minamoto-Rishima and their pH of rainwater since 1975. At Minamoto-Rishima, the rainwater is almost normal. In contrast, the rainwater at Ryolai is much more acidic. It is because Ryolai is close to the heavy industrial regions of Japan, where the air pollution that causes acid rain is much severe. Even in Minamoto-Rishima, which is far away in the Pacific Ocean, the pH of rainwater decreased in recent years due to air pollution. Acid rain is caused by acidic oxides in air. The first step of acid rain formation is the emission of sulfur and nitrogen oxides. 2/3 of sulfur dioxide and 1/4 of nitrogen oxides in the atmosphere come from the combustion of fossil fuel in power stations. Nitrogen oxides are also produced by vehicle motors and other industries. In the cloud, sulfur and nitrogen oxides react with water and oxygen to form sulfuric acid and nitric acid, both of which are strong acids. The strong acids then fall to the ground with rainwater as acid rain. Acid rain does harm to the soil, forests, and waters. Like pH, we can define pOH. It is p-hydroxide ion activity. We can find that the sum of pOH and pH is pKw. That is, the pOH of an acidic solution is over 7. The pOH of a basic solution is under 7. For example, the pOH of 0.1 mol per liter hydrochloric acid is 13. The pOH of carbon dioxide saturated ancient air is 8.32. The base dissociation constant, Kb, of a monoprotic base has a similar form as the acid dissociation constant of a monoprotic acid. A strong base is a base with a big Kb. If only one strong monoprotic base exists in an aqueous solution, the hydroxide ion activity is approximately the initial activity of the base. The pOH and pH can be calculated using the previous equations. For example, sodium hydroxide is a strong base. 0.1 mol per liter sodium hydroxide has pOH of 1 and pH of 13. A weak base is a base with small kb. If only one weak monoprotic base exists in an aqueous solution, the hydroxide ion activity can be calculated using the equation for weak electrolyte. It depends on both the initial activity and Kb. The pOH can be calculated from the hydroxide ion activity. For example, ammonia is a weak base. The pOH of 0.1 mol per liter ammonia is about 2.9. And its pH is about 11.1. The conjugate base of an acid undergoes hydrolysis to form the acid and a hydroxide ion. The hydrolysis constant is the equilibrium constant of hydrolysis. It is essentially another form of base dissociation constant. Furthermore, the product of the acid dissociation constant of an acid and the hydrolysis constant of its conjugate base is Kw. So, for conjugate acid and base, the sum of pKa and pKh is 14. A stronger acid has a weaker conjugate base, vice versa. Here, I show you the pKa and pKh of some conjugate acid-base pairs. The first thing to notice is that the difference between a pair of conjugate acid and base is a proton. Second, the sum of pKa and pKh is always 14. That is why data books only provide the pKa values. For example, find the pH of 0.1 mol per liter sodium cyanide. Sodium ion is a conjugate acid of sodium hydroxide. It undergoes hydrolysis. Meanwhile, cyanide ion is a conjugate base of hydrocyanic acid. It also undergoes hydrolysis. However, sodium hydroxide is a very strong base, so sodium ion is a very weak acid. On the other hand, hydrocyanic acid is a very weak acid, so cyanide ion is a very strong base. Thus, the pH is determined by the hydrolysis of cyanide ion. First, calculate the pOH from the acid dissociation constant of hydrocyanic acid. Then, convert pOH to pH. In another example, find the pH of 0.1 mol per liter ammonium chloride. Similarly, since hydrochloric acid is a strong acid, the hydrolysis of chloride ion is negligible. We only need to consider the hydrolysis of ammonium ion, because ammonia is a weak base. According to the dissociation equilibrium, the proton activity is proportional to the ratio of the activity of the acid to that of its conjugate base. The proportionality coefficient is the acid dissociation constant. This relation is called Henderson-Hasselbalch equation. For a dilute solution, the activity ratio is approximately equal to the concentration ratio. The pH of the solution can be calculated as well. Consider a solution made of an acid, HA, and the corresponding salt, Ba. Suppose HA is a weak acid. Its dissociation degree is low. The concentration of HA is approximately the initial concentration of HA. Meanwhile, suppose Ba dissociates completely. The concentration of A anion is approximately the initial concentration of Ba. As a result, the pH of the solution is directly calculated from the ratio between the initial concentrations of HA and Ba. For example, consider a solution of 0.1 mol acetic acid and 0.1 mol potassium acetate. The initial concentrations of acetic acid and potassium acetate are identical, so the pH is equal to pKa. If the initial concentration of potassium acetate is 1/10, the pH decreases by 1. In another example, the solution is made of ammonia and ammonium chloride. Here, ammonia is a weak base. So, the concentration of ammonia is equal to its initial concentration. Ammonium chloride dissociates completely. So, the concentration of ammonium ion is equal to the initial concentration of ammonium chloride. Here, ammonium ion is the acid, while ammonia is the conjugate base. Therefore, to calculate the pH, the acid dissociation constant of ammonium ion is used. A buffer solution is an aqueous solution consisting of a mixture of a weak acid and its conjugate base, or vice versa. Its pH changes very little when a small amount of strong acid or base is added to it. Suppose a strong acid of a small initial concentration is added to the buffer solution. The base of the same concentration is converted to the conjugate acid. Thus, the solution becomes a new buffer solution. The proton activity can be calculated. The change of proton concentration is much smaller than the concentration of the strong acid, because Ka of the weak acid is very small. Therefore, the proton activity is stabilized by the buffer solution. For example, suppose 0.01 mol per liter potassium hydroxide is added to a buffer solution of 0.1 mol acetic acid and 0.1 mol potassium acetate. 0.01 mol per liter acetic acid is converted to acetate ion. The proton activity and pH after adding the strong base can be calculated. It is found that, after adding the strong base, the pH rises by only 0.09. For comparison, if 0.01 mol per liter potassium hydroxide is added to pure water, the pH rises from 7 to 12. Obviously, the buffer solution is very effective in the stabilization of pH. Polyprotic acids and their amphiprotic ions are widely used as the electrolytes in buffer solutions. For example, in the solution of monopotassium phosphate and dipotassium phosphate, the governing acid is dihydrogen phosphate ion. Its conjugate base is monohydrogen phosphate ion. The pH can be calculated from the second acid dissociation constant of phosphoric acid. If the initial concentrations of monopotassium phosphate and dipotassium phosphate are identical, the pH value is about 7.20. In another example, in the solution of sodium hydrogen carbonate and sodium carbonate, the governing acid is hydrogen carbonate ion. Its conjugate base is carbonate ion. The pH can be calculated from the second acid dissociation constant of carbonic acid. If the initial concentrations of sodium hydrogen carbonate and sodium carbonate are identical, the pH is about 10.25. By the way, the actual pHs of buffer solutions are slightly different from the calculations due to the non-ideality of electrolytes. Here, I show you some commercial buffer solutions. Different buffer solutions have different pHs, because of their different acid dissociation constants. Amphiprotic compounds such as potassium hydrogen phthalate by themselves can be used as buffer solutions, because they can consume both protons and hydroxide ions. At the end of this section, let's discuss Lewis's definition of acid and base. Lewis focused on lone pairs rather than protons. A Lewis base donates lone pairs. A Lewis acid has empty orbital to accept lone pairs. When a Lewis acid and a Lewis base interact, they form a coordinate covalent bond and become a Lewis adduct. For example, ammonia can serve as a Lewis base because it has lone pairs. Boron trifluoride can serve as a Lewis acid because it has empty orbital. When ammonia and boron trifluoride interact, ammonia donates a lone pair to boron trifluoride. In another example, when carbon dioxide reacts with water, the oxygen of water donates its lone pair to the carbon in carbon dioxide. So, carbon dioxide is a Lewis acid, while water is a Lewis base. Lewis's acid-base theory is very important in the understanding of reaction mechanism. We will have a discussion on that topic in the next chapter. Finally, let us discuss the relationship between Arrhenius, Brønsted, Lowry and Lewis acid-base theories. Generally speaking, a Lewis base is also a Brønsted-Lowry base, because a lone pair can accept proton. For example, ammonia is a Lewis base due to its lone pairs. The lone pair can accept a proton to form ammonium ion. So, it is also a Brønsted-Lowry base. A Brønsted-Lowry base is also an Arrhenius base in aqueous solution, because the protonation by water produces hydroxide ion. For example, when ammonia accepts a proton from water to form ammonium ion, a hydroxide ion is produced. A Lewis acid is also an Arrhenius acid in aqueous solution, because the acceptation of lone pair from water produces proton. For example, aluminium ion is a Lewis acid because its 3s orbital is empty and can accept lone pairs. When an aluminium ion undergoes hydrolysis, it accepts lone pairs of hydroxide ions from water, and protons are produced.